Our first speaker in this plenary is Francisco Duque from the Max Planck Institute for Gravitational Physics. Francisco will tell us about astrophysical environment effects in extreme mass ratio in spirals.
Okay, so thank you for the introduction. If you pay attention to GRQC in arXiv regularly, you will know that the business that I'm going to talk about is kind of a hot topic. Does this work or no? No. The laser works with the to pass a slide.
I have another one to give you.
No, but to pass a slide, I think.
Oh, the slide. No. So this is the one that advances the slide. So just hit the next.
Even that. Okay. Okay. Yeah, as I was saying, this is a hot topic in the field right now, so which makes it challenging to condense it into 25 minutes. So instead, what I'm going to do is I'm going to put my hat of chair of the Fundamental Physics Working Group of the LISA Consortium and highlight the collaborative projects that are being done on this topic within the consortium. And if you check their names, they look very different from each other, but I'm going to try to show you that actually at their core, they share the same backbone and physical basis. So first, what are environmental effects? When we think of a binary black hole, the image that we have in mind is this one. So two compact objects formed from the collapse of isolated stars that are warming around in the universe. So environmental effects is what happens when this picture breaks, because you have some kind of matter or more compact objects around this binary that makes them dynamically relevant for the problem. Savik yesterday already introduced two systems where this happens. So we have nuclear clusters where the density of compact objects can be 1,000,000 times bigger than in the solar system, and you will have triple body interactions, successive mergers hierarchically. You also have accretion disks, which can become very dense when the massive black hole is actively accreting, being fed from gas around the galaxy, which also promotes compact object formation in the disk, capture from the nuclear cluster, formation of binaries and driven compact objects towards the galactic center. And then the final environment that we also think about, it's a little bit more exotic, but it's necessary for galaxy formation and evolution. It's dark matter, which can become very dense, so 1,000,000,000 times denser than the density around our solar system near the galactic center due to adiabatic contraction after a massive black hole grows. Now, if you are a sensible person, you immediately look at this and feel scared and think this looks like a mess. I've been told that the two-body problem in GR is not even properly understood. We know that our waveforms are not accurate enough for LISA data analysis, so why should we care about this? Well, it's kind of inevitable that to correctly interpret scientifically what we observe, we need to consider these effects. And this is already becoming something important for current observations. So from the almost 400 events that the LVK collaboration has observed, there is this uncovered subpopulation of black holes that is too heavy and spins too fast to be simply formed through the collapse of an isolated star in a binary. And precisely the way that these people have proposed that this is possible is that these binaries are forming in dense environments, in clusters, in AGNs, where you have second-generation black holes going with a one-generation black hole, and that explains how you can have such massive systems that should not form through the simple collapse of a supernova. So environments shape the population of black holes that we observe, but as our instruments improve and they become more and more sensitive, and this also happens for third-generation black holes, they will also start to shape the waveform signal that we see. So the impact on the dynamics that the environment has on the binary will lead to a phase shift of the gravitational wave signal, essentially. Now, if you are on the pessimistic side of life, you'll look at this as even one more source of systematic errors. that you need to care about if you want to do precision physics with gravitational waves. So if you want to test GR, if you want to do cosmology, and need to measure well the luminosity distance, if you don't account for these effects, you'll have significant biases in the recovered parameters, so that breaks those science goals. Now, if you are on the more optimistic side of things, you look at this and say, wow, this is amazing, because now I gain a new probe of physics at milliparsec scales, which I've just, in the previous talk, seen that it's very hard to probe with normal telescopes. So this is a complementary channel towards probing the environments around massive black holes that we cannot get from simple electromagnetic radiation. And these environments are necessarily tied with how massive black holes grow and co-evolve with their host galaxies, so they can also give us some information on that. Now, for current detectors, this effect on the waveform is still too small. We need a lot of cycles so that the effect accumulates over many orbits, and that's why extreme mass ratios spirals are a canonical system to look for these effects. So MRIs, they will complete tens of thousands of orbital cycles in a little observation window, which makes it, and they can have these very rich waveforms in their harmonic content, which is both a problem for modeling and for data analysis, to solve something that evolves in such a rich way for so many orbital cycles. So the way to do that is to expand the Einstein's field equations perturbatively in a mass ratio between the small black hole and the big black hole. This is the whole self-force program and black hole perturbation theory. But then you need to be able to efficiently generate waveforms for such a long time scale. Fortunately, or at least the way to do it, is the fact that there is a separation of scales between how fast the phase is evolving. Okay, this doesn't work. How fast the phase is evolving, and which evolves on the orbital timescale, and then the slow timescale of the problem, which is in which these amplitudes and the frequency itself is also varying, so the energy and angular momentum of the binary. So if you do the separation of scales, you can pre-compute all the things that need to be computed within the orbital timescale, and then you do a secular, to consider the secular evolution, you can just do a sort of coarse interpolation of the orbit on the fly. And this is the basis of the fast MRI waveform package, which is the state-of-the-art package to do waveform generation. And you see the structure occurring a lot for the rest of the talk, where we need to compute things that cost a lot offline, store them somehow, and then we evaluate waveforms on the fly through the secular evolution. So the great thing about MRIs is that even though they are hard to model and hard to analyze, the tens of millions of overlapping tens of thousands of cycles means that we can constrain the parameters of the system extremely well. Like we can constrain eccentricity with a relative precision of 10 to the minus 5, same for the black hole spin. And that's why then they become so sensitive to the presence of environmental effects. And this has been recognized explicitly as a science objective in the LISA definition study reports, and we're even building a figure of merit for it. And it's not, although I will focus the rest of the talk on MRIs, it's not the only case where this can happen. There's also scenarios for stellar mass binaries, and at least the low-hand tail of the LISA massive black hole binaries, where the spiral is also quite large. You can also have interesting environmental effects there. And in this last case of the LISA massive black holes, this connects also with multi-messenger astronomy because they will be affected by disks. So by now I hope to have convinced you that you should at least be considering this problem. So now how do we actually model these effects? How do they enter our waveform models? So let's consider our MRI. And perhaps the more intuitive environmental effect to consider is the third body interaction, the case of the nuclear cluster. So we're going to put one more object there, and this object is sufficiently far away from our original MRI and not so massive that we can study its tidal perturbation on a perturbative matter, so to the two-body dynamics of the MRI. Now this tidal force will oscillate with the period or with the frequency that is the difference between the frequencies of the two orbits of these two objects. Now, this oscillates around 0, so the secular effect generically will be 0, except when these two frequencies match. When this happens, you have a case of the resonance, and this will lead to a sudden jump in the parameters of the MRI, so it's energy and angular momentum of the orbit. Now, if you didn't, this is ubiquitous in planetary dynamics. It explains, for example, why the moons of Jupiter have such volcanic activity. If there were no gravitational waves, this resonant exchange would just be going up and down between the two bodies. But here, because we have an inspiral, our MRI will pass through the resonance, and then continue its inspiral out of the resonance. So you have really a jump, and you don't go back to the original state. Now, if you ignore this, you'll have bias parameters. This has been seen, and this problem for modeling is also this happens on a different time scale of the problem. So this simple 2 time scale expansion does not work. You have to introduce something else. So this arrives me to the first consortium project that I want to mention, which is a collaborative project between the fundamental physics and the waveform working groups, where people are trying to build these models for jumps, pre-compute them, and then add them to the fast MRI waveform package. And they are building 2 codes. One solves the orbital dynamics on the orbital timescale. It's a slow, accurate oscillating elements code that can serve as a baseline for the problem. And you can actually do this generically for other environmental effects. And the other is a way to predict within a few framework when these resonances will occur and have a cheap way to at least evaluate these jumps. And at least they already have something working on for a toy model, and probably within the next 6 months, something more robust will come out of it. Before I move on to the next environmental effect, I also want to mention that in the case of triple systems, there's also this class of systems called B-MRIs, so binary MRIs, where you have a small stellar mass binary orbiting around a massive black hole. In this case, in addition to interesting three-body interactions, you also have propagation effects. So when the binary is behind the massive black hole, you have amplification due to lensing. When it's coming towards us, you have a Doppler effect and aberration and so on. I will not go into detail here, but if you want to look into more detail, check the references. Okay, so this finishes the part of tidal resonances. And in fact, I could finish the talk here because the rest is just repetition. So imagine that now we don't have a single body or a third body. We start adding more and more and more. So some of these will fall into my MRI, and in this case you have accretion. But because the stellar mass black holes have such a small cross-section, this effect is not that dynamically important compared to the others, which is the fact that now you have a sum over a lot of tidal resonances. And now if you take the continuum of having a continuum of particles around my MRI, what you have is a cloud of particles, and if you ignore that they are interacting between each other, you need to basically integrate all the tidal resonances from this cloud of particles over the phase space distribution describing this cloud. So it's probability that one particle has some energy and angular momentum. Now this might not be obvious, but a collisionless cloud of particles that is coupled only to gravity is precisely dark matter. And this integral over the phase space distribution is a global version of what will be dynamical friction, where dynamical friction is a local version of this, where you approximate on the frame around the secondary, and you consider only scattering of particles. But if you try to do this in a global version, you really arrive at the same result. And this has been seen in the Newtonian limit. And now people are attempting to do it in the relativistic regime, but it's a very hard problem. So at least at the relativistic way, what has been done and accomplished so far is to do this relativistic extension of the local dynamical friction, or to consider an effective description of dark matter in terms of fluids, where you then use techniques from black hole perturbation theory that are very analogous to what is done in relativistic stars. Now, in both cases, in both these approaches, what has been seen is that when you model these things relativistically, you get an amplification of the effect that the dark matter distribution has on the evolution of the emery in a strong field gravity regime. So the effect can be 10 times stronger than what the Newtonian estimate suggests. Why this is happening? Well, you can imagine that you have your emery in a circular orbit, and then you have a third body also in a circular orbit. So the emery is essentially making oscillations of the third body around its central orbit. Now, we know that as we approach the ISCO, or at least at the ISCO, if you perturb objects in the ISCO, the perturbation will grow exponentially. So it makes sense, at least physically, that as you approach this quasi-stable scenario, that this amplification is also growing. And this explains why in the relativistic regime you get this amplification. Now, this is good, at least if you care about this, because if the effect is stronger, it's more relevant for observations, and you can put bounds on the dark matter density from observations of emeries in these systems. And we don't know if these dark matter overdensities exist, but if we don't observe any with emery observations, this at least tells us something about how massive black holes grow, how often they are merging within the edge of the universe, what's the effect of the dynamics of the cluster in this dark matter distribution. And so at the level of the LISA consortium, what is being done is to try to unify these effective dark matter descriptions, so this local dynamical friction with this fluid-like description, and then generates all these data sets for the energy flux or corrections to the energy flux and angular momentum for the emery, and integrate them into Fuse so that they can be analyzed with future observations. And I'll say something about this more at the end. So how am I doing on time? Okay, perfect. Okay, so now moving to the next environment. I try to draw this in a way that if you look at it, what it should remind you is almost like an atom. At least a Niels Bohr version of an atom where you have concrete orbits. So in this particle-like description of dark matter, this only works if the de Broglie wavelength of the dark matter particles is much smaller than the black hole size. Now, what will happen is that if you consider successively less heavy dark matter particles, so lighter particles, at some point, this de Broglie wavelength will start to become comparable with the black hole horizon size. And when this happens, you no longer have a particle-like description, and you gain a wave-like description of this structure. So you don't have a distribution function for the particles. What you have is a wave function. Now, this historically, this wave dark matter has been proposed for two different reasons. The first is that at least on the very light end, ultralight end, with 10 to the minus 23 electron volts, this could explain or this could cure the cusp that we observe in dark matter simulations, because then you have a flat profile of dark matter. So this is what is called fuzzy dark matter in comparison to cold dark matter. But then it also became relevant more in the context of beyond standard model physics, and even string theory, where these scalar fields can be justified. Now, what happens in this case, where the mass of the dark matter field is, or at least this Compton wavelength, is comparable to the black hole size, is that you can have a resonant extraction of angular momentum from the massive black hole, and the field grows into these very dense clouds that can be like more than 1 million times denser than an AGN disk. So this is what's called superradiant. And they really have a structure that is very similar to the structure of the hydrogen atom. So now, when we think about tidal resonances, it's almost the same thing as thinking about transitions between orbital states of the atom, or in the case where the energy that is given from the binary to the dark matter field, if it's too large, the field can leave its bound state and sort of have ionization. But at the core, this is really the same as we have just seen. It's just now I don't have particles, I have a scalar wave equation for dark matter distribution. Now, when people have modeled this, they have again seen the same thing as before, that in the relativistic regime, you have an amplification of this effect by an order of magnitude, which again makes it more relevant. And something that is quite interesting here is that because now the black hole becomes sensitive to the scale of the dark matter field, this means that it can distinguish between the size of the particle. So, and this size is directly related with its mass. So now, if you try to analyze this in mock LISA data, you can no longer just constrain the dark matter density or the mass of the clouds, but you can really constrain the fundamental mass of the field when you are in this regime. So at the level of the LISA consortium, what is being done, so this system is probably the simplest one to understand, at least at the fundamental level, because you are just solving the Einstein-Klein-Gordon equation. So this has become sort of the playground to try to do the modeling of MRIs in astrophysical environmental effects at a very rigorous level within the self-force framework. And this is what is being pursued there, so that it can then be used and applied to the other environments. And after this is well done, you will repeat the same steps of generating fluxes for these systems, add them to Few, so that they can be used for data analysis. Okay, now I've talked about triple systems. I talked about dark matter. The one that's missing is accretion disks. So the two important words here for dark matter is collisionless and only coupled to gravity. So now if you relax these two assumptions, you get an accretion disk. So if you have a collisional gas that also couples to electromagnetism and that can shock and radiate away the energy, that radiation of energy will make the particles in the disk collapse to the low energy state, which is precisely an equatorial disk in circular motion. And that's how you form a disk. No, so even though that's at the microphysical level, it's a little bit different, in the end, the same resonance structure can be translated from what we had before. And in fact, recently, there were 3 works modeling these systems in the relativistic regime, and they used different techniques, but very similar machinery that was done to model MRIs in dark matter spikes and in dark matter clouds. So again, here you have amplification in the relativistic regime. Something quite interesting that we also saw. So we all saw this is that we have an inversion of the sign of the disk torque on the MRI close to the ISCO. So instead of accelerating the spiral, the disk is stalling the spiral. Unfortunately, this happens so strong in the field gravity regime that's probably not very relevant for observations, but still interesting to observe it. And now this amplification again changes what LISA can observe, because it makes LISA capable of distinguishing between different configurations, so different densities and how fast the disk is being accreted by the massive black hole. This directly relates with also how bright the disk is. So an angle that we are interested in pursuing further is how you can combine information from the environment through the gravitational wave channel with cross correlations with the electromagnetic channel. So if I know through the gravitational waves that my MRI is in an AGN disk with some kind of luminosity, this can make me perhaps eliminate what are the possible host galaxies within the localization area of the MRI and improve measurements of the Hubble constant through the dark sirens methods, as we heard yesterday. So these models were done in a very simplistic laminar-like regime, but AGN disks are very complicated, as many talks here are pointing out. In particular, they are turbulent, they have stochastic variability, and something that we are trying to do in our project of the LISA consortium is to try to hybridize these analytic methods with hydrodynamic simulations. So in principle, you can take this variability as a source of uncertainty, and you treat it as an envelope. So in the same way that calibration errors are done in waveform modeling against numerical relativity, and then you can probably marginalize over this uncertainty. So this is what we are doing in the project that I'm coordinating, and the final thing that I'm going to talk about is actually how you do this in practice to then confront it with data. So, you know, I come from theory where things are very nice, but after working for 3 years with Jonathan Gare, he collapsed all my hopes and dreams. by showing me how data analysis for LISA is so hard. So in particular, we need this global fit to disentangle the tens of millions of overlapping signals in LISA, and you will hear more about it tomorrow. But now I'm telling you that we need this global fit and multiply it by all the physical scenarios that can be interesting, and I mean, this is just impossible to do, both technically and computationally. You'll lose almost as much energy as the one that is being wasted to cool down this room with the AC. So the expected way to do this is to first do the fit using vacuum models, and then post-process the catalog that the ground segments build to try to search for these effects. And now, how to do this in practice? I have some suggestions. I cannot go into detail on them, but I urge you to all think about it. But what I want to finalize with is that just directly comparing the data against all the physical models itself is not even feasible, even at the post-processing level. So what we are pursuing is we're trying to build phenomenological waveforms that are flexible enough to fit the data without committing to a specific physical model. So the zeroth order iteration of that will be a power law fit of these effects. And this seems to work kind of well, at least for the case of the accretion disk. This has work that has been done by Lorenzo, who is on the room. So here you see essentially the fractional power that is left if you try to fit with the power law model over against the physical model. And it's, at least for the SNR that we expect to see to observe MRIs, is not significant. But then we are faced with the question of how you can then map the parametric models to, or the model agnostic models to the physical models. You can do this perhaps learning the inverse map with some kind of neural network, doing reweighting against a different parameterization. But I'm already over time to go into that. So the final most important question is that, or at least what I try to convince you, is that this is a subject that is very challenging, but it's also very rich physically. So you have almost all fundamental constants of nature involved in the problem. You have different techniques being necessary to solve the problem. And this is really the situation where something like the consortium shines, because it brings together people with different backgrounds that can tackle these challenging problems in an interdisciplinary way. So I'm going to shut up, and you're going to clap because you are polite, but do it not just for me, but also to thank all the great work that is being done by all these people.
Do we have any questions? Call first, Shane second. First, Shane second, or go ahead, Shane.
I can go first, yeah. Okay, thanks, Francisco. That was great. You know, I think what you said here at the end in terms of, you know, going phenomenologically and being model agnostic kind of will get us to the point where we can do analysis. But in the end, we ultimately want to extract some science about these environments. So if I look at this entire landscape, is one of these the one that we have the most likelihood of understanding first and making the most progress on before LISA, if we want to focus on one of these environmental effects that's going to be the most important astrophysically?
Depends on who you ask.
Okay.
I mean, so I'm going to say various answers to that question. So we know that accretion disks exist, so that will be one to focus in particular. But we also know that they are the harder ones to model. Tidal resonances, we at least also know that clusters exist. And those are probably a little bit easier to understand. Now, probably the more interesting, if you want to win a Nobel Prize, is to go for the dark matter ones. And at least in the case of the boson clouds, they're also where at least they have a pedagogical value in the sense that they are the easier to understand at the formal level. So many, as I said, many ideas that we used for the accretion in this case come from years of work on the boson clouds. So I would say that considering how transversal the techniques are, it doesn't make sense to just focus on one, because really at their backbone, they are the same. They are just resonant interactions of particles or of a state with the MRI. Yeah. think I gave a politically correct answer.
This is extremely varied and exciting science. When you're thinking about learning about the accretion disks, what are you assuming regarding how long you can maintain a coherent waveform? Is it, for example, years? Because that's a lot of cycles to get straight.
Yeah, so that's a very good question, and I usually don't say this. Because, so you are thinking about the turbulence, right? The fact that you have a turbulence that typically has a correlation length of 1 orbit or 100 of orbits. Now, the way I envision it is that you will have oscillations of this turbulence around a baseline value, and this can be a strong assumption. If you have this, I think you can still extract sort of the secular linear term with some uncertainty. If this turbulence is so strong that you don't have like a reference background disk, I think that's a much harder problem to understand, and it's not something that I think will be easily doable. But we are trying to, so a way you could do it is you have a turbulent flow with some energy spectrum and some kind of characteristic correlation length, and you can add this in this sort of multi-scale expansion of the MRIs to the right-hand side of the equations. Now, how much you can actually learn from that with one observation, I don't know. Probably not much. So it will be just a source of uncertainty in the model. Now, if you observe, let's say, dozens of hundreds of MRIs in accretion disks, maybe you can then do a statistical characterization of this spectrum.
More question from Chiara.
Thank you very much for the talk. I had actually 2 questions. The first one is, what is the range of mass that you can probe of ultralight dark matter mass? I've seen you had a 10 to the minus 17 electron volt, I think, there for yours. But I suppose you can probe some range of this, but maybe not too wide.
So we can probe between, so here, between 10 to the minus 13 electron volts or 14 electron volt, and let's say with LISA 10 to the minus 16, 17 will be the maximum, because this is when the Compton wavelength of the field is comparable to at least with one of the sizes of the black hole, either the primary or the secondary.
The other question I had concerned, so did I understand correctly that these accretion disks are the accretion disks formed of dark matter?
No. This is
okay.
gas, sorry.
Gas, okay,
Yeah.
okay, sorry. Thank you.
Yeah.
Okay, thank you. Let's thank the speaker again. Our next speaker is John Ruan from Bishop's University. He will tell us about the challenges and strategies for telescope follow-up of LISA massive black hole binary mergers. Take it away.
Great. Thanks, Tamara. Hi, folks. I'm an observational astronomer, and I'm going to tell you a little bit about what I think the challenges and strategies for telescope follow-up of these massive black hole binary mergers that LISA will detect, what that will look like. I want to thank the conference organizers, but also Maria for providing much of the intro for my talk. Also note that my talk is biased towards optical stuff because I saw that on Thursday, Krista will be giving a talk on X-ray stuff, so I'll leave the non-thermal stuff to her. Okay, so some very brief background. So the massive black hole binary mergers that will be detected by LISA result from galaxy mergers, right? So you have 2 galaxies, each of them, both of them have a massive black hole at the center. So the galaxy merge, and over time, the two massive black holes will experience dynamical friction and find each other. They will sink to the center of the gravitational potential. And skipping over a lot of details regarding things like stellar scattering, gas torques, overcoming the final parsec problem, the 2 massive black holes will eventually form a gravitationally bound binary system and emit gravitational waves and coalesce, and that'll be detected by LISA. Okay, when LISA makes this detection, it'll be very interesting to use your telescopes to find the electromagnetic counterpart, the exact one, whatever it may be. I'm still being agnostic at this point. So for example, it'll be interesting for gravitational wave cosmology using bright standard sirens. We had a talk about that yesterday, so I won't talk about that. If you can identify the counterpart and it's a binary that is actively merging, actively accreting, then you can study the circumbinary accretion flow, and you can also probe the co-evolution of these massive black holes in their host galaxies, right? So for example, there's things like scaling relations, like here, the M sigma relation between the black hole mass, which you can get from the gravitational waves, and the host galaxy stellar dispersion, which you can get if you can identify the host galaxy. And if these sort of scaling relations are thought to be due to the co-evolution of the galaxies and their central black holes, so you can study how these scaling relations change as a function of redshift, right? But for all of these, interesting science cases, you have to be able to identify the electromagnetic counterpart. So the question is, how do you do that, right? So I'm showing you here a LIGO sky map that you've seen before, and this is one of the nicer looking ones. It gets a lot more messy than this, and in this sky localization region, there's a lot of stuff. So for LISA, what does LISA give us? Similarly to LIGO, it gives us a sky map. It'll give us a distance posterior. It will tell us the time to merger, when the merger will occur, and it'll give us masses. Okay, and so then the question is, okay, so how do you actually identify the electromagnetic counterpart? Well, it really depends on what the counterpart is, like what are you assuming that it is? So I'm going to talk about 3 cases. So first is a transient counterpart, so there's some sort of transient associated with the merger. The second is a circumbinary accretion disk, so if the binary is actively accreting. And the third one is just of the host galaxies. Okay, this is sort of a false dichotomy or a trichotomy, I guess, because all 3 of these could be true at the same time, right? They're not mutually exclusive, but I'm going to explain them one at a time as if they're mutually exclusive. Okay, so first focusing on the transients. So what we're assuming here is that there's some sort of transient associated with the merger. Okay, so do we expect transients? Yes, there are many, many theories on transients that are expected from massive black hole mergers. I'm just showing you just a very small selection of them. So for example, if the binary is actively accreting and there's a circumbinary disk, at the time of merger, there's mass loss due to gravitational wave losses. You can get a recoil kick on the remnant, right? And the disk will respond to that. And you can get like a long-lived afterglow due to that. There's things like, for example, in the circumbinary disk, the inner cavity will sort of viscously infill after the merger, and that could make the AGN brighter. You can launch jets, et cetera, et cetera. This is not any sort of complete compilation. But the point I do want to make is, from an observational standpoint, none of these mergers haven't really converged. Right? We don't really know what we're looking for, and I'm illustrating that by using this compilation of light curves associated of transients associated with massive black hole mergers that I've made. So these are light curves. So the x-axis is time since merger from something like an hour after the merger out to months after the merger on the right. The y-axis is luminosity. And the black lines are just various models that I found in the literature for what the transients would look like. And the point here is that they're all over the place. They can look like anything, right? This is sort of different from looking for kilonovae counterparts to binary neutron star mergers detected by LIGO, right? But because for a kilonovae, for the LIGO case, for kilonovae, we sort of know what their luminosity is. We sort of know that their light curves will fade pretty quickly. They'll be pretty red because of the high opacity lanthanide elements. For massive black hole binaries, we haven't really converged on a model. So you sort of have to stay model agnostic here. And of course, in the sky localization region, there's also all kinds of other transients as well, the more normal transients like supernovae and things like that. And so we will have to sort of comb through the haystack to find the needle. And if we don't actually know what the needle looks like, it actually sort of becomes an anomaly detection exercise. Okay, so how many transients, these unrelated transients, do we expect? So how big is this haystack? That's sort of shown on the plot. So let's start with the left plot. is showing you the number of transients in an expected LISA localization region as a function of time. So time to coalescence starting from a few days before the merger down to the time of coalescence. And of course, because the sky localization region shrinks over time, the number of transients in that sky localization region decreases over time. So on the left plot is showing you a case at low redshift. If you don't have redshifts of all of the transients that you detect in the localization region, then all you're contaminating transients is everything along the line of sight, right, to that two-dimensional localization region. And there's a lot of them, right? So that's shown in the red line. So at the time of coalescence, you would expect something like a few hundred unrelated transients. So that's how big the haystack is. Now, if you actually have the redshifts of all the transients, you can throw out most of the contaminating transients, because then you can use the difference information from the gravitational waves to only consider transients in that three-dimensional sky localization volume, which is much smaller, right? So you're no longer looking at everything along the line of sight, and instead you're only looking at in that localization volume. And so that's shown in the blue there, in the blue line. So at the time of coalescence, you get less than one unrelated transients, which you might think, oh, great, so problem solved. But however, that's not true if you're looking at higher redshifts. So in the middle panel, that's at redshifts, around 1 or so. On the panel on the right, that's at even higher redshifts, around 2, greater than 2. And the point here is that, for example, if you look at the Mojito data set, all of the massive black hole, nearly all of the massive black hole mergers are at higher redshifts, right? So only, looking at the low redshift case is not realistic. So what I'm saying is that there will be a lot of contaminating unrelated transients. We will have to sort of sift through that haystack. Oh, and these are some calculations that my grad student David Corentin is working on. So how do you sift through that haystack? So if you accept that, yes, there will be unrelated transients in the sky localization volume, I think you'll have to do some sort of anomaly detection, outlier detection exercise. And there are ways to do that, right? So this is just an example of, you can do this by on your light curves of the transients by training a variational recurrent autoencoder, which takes the sort of qualitative properties of your light curves and reduces it down to a low dimensional latent space where you can do outlier detection. I won't get into this, but there are ways to do this, okay? All right, so that's for transients. Moving on to what about for circumbinary accretion? So in this case, we're assuming that the binary is actually accreting and there is a circumbinary disk, right? So simulations have long shown that, the circumbinary disk has this sort of structure where you get a cavity on the inside and there's many disks around each of the two black holes and there's streams, et cetera, et cetera. However, many of these simulations have predicted that you should see periodicities in the electromagnetic emission. So, for example, in light curves, you should see periodicities from things like accretion rate modulations from the lumps in the disk, like you sort of see a lump in the disk in the simulation. There could be Doppler boosting of the mini-disk emission around one or both of the black holes. There could be self-lensing of the disks where one black hole moves sort of behind the other and the mini-disk emission is lensed by the other black hole. There could be periodic jets, et cetera, et cetera. But the point is that there could be, there's many models for periodicity. So it is interesting to look for periodicities, and especially because, if your localization region is large, you want to be able to use, and you want to use time domain information, you want to be able to use these wide field time domain surveys like Rubin LSST. Okay, so there's a long history of looking for periodicities in light curves that Maria already covered. This is just a pretty well-known example of a previously claimed periodic AGN from like a decade ago now. But how would you do this in LISA? So for LISA, you would still contend with the issues of the stochastic variability of normal AGN. So even for normal AGN, even without a binary in them, they're still stochastically variable. And they have a periodic component on top, so you would have to somehow disentangle that. Maria explained how difficult that can be. Some people have suggested things like, for example, you can use the gravitational waveform as a sort of a template for your optical search. So if you assume that, the periodicity in the optical light curve has a similar period or period evolution, or even if it's like phase locked to the gravitational waves, that makes the search in the optical light curves a lot easier. I tend not to like that because in my view, the search for periodicity in the optical light curves should be more flexible and make minimal assumptions, because I don't think you want to necessarily assume that the optical periodicity has the same period and period evolution as the gravitational waves. I don't think you should assume that they're phase locked, right? Because I mean, the gravitational waves are from the binary, the orbit, whereas the electromagnetic emission is from the gaseous environment, and they don't have to be phase locked. They don't have to have the same period. They don't have to have the same shape for the periodic component, right? Like, it doesn't have to look sinusoid. It could look like flares. It could look like other things. So how do you do this search for periodicities in light curves while making minimal assumptions? So my postdoc, Wei Xiang, has been working on this, and so he has this new code called EasyTau-X, which models multi-band light curves of AGN using Gaussian processes to look for periodicities. And this is just showing an example simulated Ruan LSSC light curve of AGN. So there's 2 bands here. LSSC has more bands, but here I'm only showing 2. And he does this modeling to look for periodicities using Gaussian processes. So he models this using Gaussian processes, and in the kernel for this Gaussian process, it includes a damp random walk, and as well as a Lorentzian, which takes into account a quasi-periodic component in the light curve. So here I'm showing you essentially a power spectrum, a PSD, and so this is PSD as a function of frequency for the damp random walk component, which models the stochastic component of the light curve, as well as on the bottom is the Lorentzian. You can see it has a sharp peak, which picks out the periodicity, but it has some width as well, so that you can pick out quasi-periodicities, and also the width allows you to pick out periodicities where the periodic component can have any sort of weird shape. So it can pick out flares, it can pick out sawtooth patterns, et cetera. So not just sinusoids. So, and also this code is JAX accelerated. So it's very, very fast, blazingly fast, and it's scalable to LSSD data volumes. And this is just an example of some tests that we've done. So this is a simulated Ruan LSSD light curve that's stochastic, plus it has an underlying periodic component, which is shown in the faint gray, so it looks sinusoid. And yeah, and on the right is the PSD where we show that yeah, you can pick out the peak there. Just note that although I'm showing you PSDs, we are not taking Fourier transforms at any point because the modeling is done using Gaussian processes in the time domain. But I am showing you this PSD just to show you that yes, we can pick out the periodicities. It's purely for visualization. Okay. What if the periodic component is not a sinusoid? So for example, what if it's kind of like a sawtooth pattern, which you might expect from accretion rate modulations from the lumps in the circumbinary disk? We can do that as well. We can pick out the period. What if it's flares? We can do that as well. So you might expect flares from, for example, self-lensing. We can do that as well. Okay, so moving on. Let me check the time. Okay, doing fine. Okay, so moving on. What happens if the binary is not actually accreting, right? There's no guarantee that the binary is actually accreting or you will see any of this. Even if it was accreting, the accretion could be dust obscured, so it would be an obscured AGN, which makes it, so for example, you wouldn't necessarily see the optical variability or the periodicity. And overall, as Maria pointed out, our understanding, our models for the signatures are just uncertain. So if it's not accreting and for example, there's no transient signatures, then you're sort of stuck looking at the host galaxy, right? So that's the last part of what I'm going to talk about. So if you look at the host galaxies of LISA massive black hole binary mergers, are there any distinct properties there? And you do expect a lot of host galaxies in these LISA localization volumes. So yesterday, Tamara told us that, well, if the merger is at relatively low redshifts of, I think, like 0.3, then the localization volume, especially at the time of merger, when all the data comes in, is small enough that you might expect only one, right? So you might have only one distinct host galaxy. But that's only true at like low redshifts. And if you go to higher redshifts of greater than 1, then you'll have multiple host galaxy, a lot of host galaxies. Or if you're interested in trying to identify the host galaxy, not at the time of merger, but say a week beforehand, where the localization region will be bigger, there'll be a lot of host galaxies. So you might expect something like, hundreds to even up to thousands of possible host galaxies in the localization region, and various people have done different calculations of this. But the question is, does the correct host galaxies have any distinct properties? And we've taken a look at this using cosmological simulations. So we use the Romulus 25 cosmological simulation, which is a cosmological volume. So you grow your galaxies in a cosmological context. The galaxies have black hole seeds, and the black holes grow through accretion and mergers over time. And in the simulations, we pick out the galaxies that host massive black hole mergers. Okay, that are detected by LISA, detectable by LISA, so they're relatively low mass galaxies. And then we also pick out a sample of galaxies that don't host massive black hole mergers as a control sample for comparison. Okay, and the control sample is mass matched and redshift matched to the massive black hole merger hosts. Okay, so on the top, I'm showing you a selection of images of the massive black hole merger host galaxies, and the bottom row are a selection of control galaxies. And the question is, do you see any differences, right? So that's what we're doing here. And how we do this is we pick out the simulated galaxies in the simulation, and we make synthetic observations. So we do ours. If you're into simulations, we do our stellar population synthesis, we do our dust radiative transfer, and we make synthetic images, we make synthetic spectra, et cetera. This is some work that was done by my former undergrad, Jane Burdatti. Okay, so, but then the question is, okay, wait, hold on, do we actually expect any distinct properties of massive black hole merger host galaxies? And the answer is yes, because these host galaxies, these binaries form through galaxy mergers, right? So in the past, there was a galaxy merger, and these LISA host galaxies are smaller, and so the galaxies are gas-rich. So you had this gas-rich merger, and then during that gas-rich merger, you might expect some sort of burst of star formation because the galaxies are so gas-rich. And then some time later, up to giga-years later, the two black holes will merge. Okay, so when LISA detects one of these mergers, sometime in the past, maybe up to giga-years in the past, you might expect a burst of star formation, a starburst in the past. Okay, is this true? Well, when we look at our simulations, the answer is yes. Right. So I'm showing you star formation histories of from the simulation of the massive black hole merger hosts in the red. So hold on. So in the x-axis is look-back time from the merger. So on the left there at look-back time of 0, that's when the merger occurs. That's when the LISA detection is. And then going back in time is moving to the right. On the y-axis is the star formation rate, okay? So for the massive black hole merger hosts that's in the red, you can see something like 2 giga-years before the merger, there was a huge spike in star formation. That's a starburst. And then closer to the merger, closer to the LISA detection, so when LISA makes its detection, the star formation rate is now very low. So that galaxy is now quenched. Okay, and this is in stark contrast to the control galaxies in the blue, which they more or less trace the cosmic star formation history, and so at the moment their star formation rate is still pretty high. So in a nutshell, what this is saying is when LISA makes its detection, the host galaxy is this is suggesting that the host galaxy had a starburst a couple giga-years ago and is now quenched. Of course, observationally, you can't probe star formation histories directly, and so you would do things like, for example, look at spectra. So if you get rest frame optical spectra of all the galaxies in this localization volume, you can look at spectral indices such as the 4,000 angstrom break and the H delta equivalent width. So the 4,000 angstrom break on the x-axis here probes a more or less a sort of a current star formation rate, whereas the H delta equivalent width probes the star formation rate a bit in the past, so maybe like 0.2 giga-years or so. But what this is showing is that the merger host galaxies in the red here have low current star formation rates, and they also have lower star formation rates in the past, recent past as well. And this is, again, exactly what you expect, right? So because these merger host galaxies are now quenched. They had their starburst in 2 giga-years in the past, and they are now quenched. And so you might be able to actually at least help prioritize LISA host galaxies this way, but just purely by looking at their host galaxy, looking at the host galaxy properties. Okay, and this is some work led by my undergrad Alison Supernon-Koch, who is actually here, and she has a poster, so I encourage you to stop by her poster. Okay, so these are my conclusions. So for transients, I told you about how if you're looking for transients, you will be contaminated by unrelated transients, and photometric redshifts are going to be important, and then you're probably going to have to do some sort of anomaly detection. For circumbinary accretion, I told you about how if you're going to look for quasi-periodicities, which I think is a good idea, but you should use methods that are really flexible and make minimal assumptions. You don't want to assume too much about what the periodicity actually looks like. And for host galaxies, what I think is that the host galaxies of these LISA massive black hole binary mergers were probably now quenched, and they had a star formation in the past. And that's one possible signature that we can look for. However, again, I want to emphasize that in practice, when LISA actually makes a detection, we will probably have to use a combination of all of these approaches, right? And it's entirely possible that you get both circumbinary accretion and some transient, and you get to look at the host galaxy. You will have to use a combination of these approaches. And what that means is that we should engage a broad community of people that have very broad expertise, right? So I've talked about things like transients, I talked about AGN, I talked about galaxy evolution, et cetera. And all of those people have to lend their expertise and pitch in. So I'll end there. Thank you.
Thank you. Excellent talk. So let's start from this side of the room and move to the left.
Thanks for the nice talk. I was wondering for the second point, what are the parameters which we can only fit, like what are the parameters, free parameters we have, which we cannot infer from M sigma or other things? Like what are the uncertainties on those?
Are you talking about?
The Gaussian model you have?
This? No.
The flexible model you have?
Okay. What are the three parameters?
So I'm asking what kind of free parameters you are going to fit when the real data comes.
Free parameters, yeah, okay. So, I mean, there's the standard so the kernel includes a dampen and walk, right? So there's the standard dampen and walk parameters of like the characteristic time scale, and there's an amplitude parameter in there. And then you have parameters for the Lorentzian as well. So for example, this is showing the differences in the quality parameter, which controls the width of that and how sharply peaked. And of course, that is purposely so. You want to have that parameter because that allows it to be flexible enough to pick out things that are quasi-periodic or has some weird shape for the periodic component with some weird light curve shape. Yeah. Okay.
Next question is from Savik.
Hey, John, very nice talk. I actually had a question also about this modeling. Actually, all right, I'll limit myself. So you have multiple bands in principle from LSST. If you are seeing something that is the effect of a binary, the binary should be in the center of the circumbinary disk, more or less. And the temperature of the disk should fall off. And so you should see if there is something that is due to the binary, then it should propagate out in some predictable fashion with respect to waveband, especially if you're going from U to Y. Can that also help us? And do you have any kind of information about the multi-band nature and the time delays between bands in your modeling?
Yeah, so we are able to do multiband, and of course, by doing multiband, you have to stick in some lag in there, right? Interband lag. We have a very simple model for interband lags where you just assume they're basically free parameters, and so we don't make any assumptions on things like, oh, if it's actually a binary that it has to have this form of lag. We want it to be as flexible as possible.
Okay. And then actually my other question, which I will ask is, so LSST covers the southern hemisphere. LISA sees the whole sky. What do we do when we don't have LSST? Or, yeah, what do we do?
I don't know. But it's possible Roman might help. I don't know. Yeah.
So let's take one more question on this side. Go ahead. We have time for multiple questions.
Thank you for the great talk. I had a question about the host galaxy properties and kind of how to tell mergers apart from isolated galaxies. And you did this work with cosmological simulations. I'm wondering if you're considering and if it's possible or plausible to use like post-merger catalogs from DESI or from Roman and looking for maybe like asymmetry, concentration, and also like the star formation histories. So just augmenting this with observations of dwarf galaxy post-mergers.
Yeah, so you know, my student Jaden actually looked at things like morphologies and stellar kinematics using these simulated galaxies, and we did find that they're distinct like morphologies and stellar kinematics, but they're mostly relevant for, so for example, merger host galaxies tend to have a bigger bulge and they tend to have more complicated stellar kinematics, but that's actually mostly for supermassive black holes that are relevant for PTAs, and I think that's because those properties are more commonly associated with dry mergers, so gas-poor mergers, whereas for LISA, the galaxies are smaller, so there'll be more wet mergers, and so to me, it's probably the past starburst that's most relevant.
We have an online question.
Yeah, the question is from Alessandra De Rosa. She says, thanks for the talk. Do you think that X-ray spectral signatures or variability studies could provide an effective route to identifying binary supermassive black holes, even if they appear primarily as variable rather than transient sources?
I don't think I fully heard the question. I didn't hear the question very well.
I'll repeat it. She says, do you think that X-ray spectral signatures or variability studies could provide an effective route to identifying binary supermassive black holes, even if they appear primarily as variable rather than transient sources?
Okay, so X-ray. Okay, so I purposely didn't talk about X-rays in my talk because Krista is going to talk about them. But yeah, there are X-ray signatures as well that don't depend on transient emission. Like, so for example, like Tamara's group has done work on things like the iron-K alpha line and things like that.
Cool. We have another question. No? That question has gone away. Okay, everyone understands everything. Excellent. Cool. Let's thank John once more for an excellent talk. Our final speaker of the session is Deborah Ferguson from the University of Rhode Island, and she will tell us about LISA, early career scientists.
Okay, hi everyone. I will definitely be letting you get to lunch early because I see no world in which this update will take the full half hour, but I just wanted to give you guys a bit of an update today on what LECS is, so the LISA Early Career Scientist Group, who we are, what we do, why you should join it, et cetera, et cetera. All right, so I'm presenting on behalf of the other ECS chairs as well, so Florentina and Albin, who unfortunately could not be here today, but who have done a lot of this work as well. All right, so first of all, what is LECS? I put the L in parentheses because we used to be called LECS, but now all of the groups have kind of dropped the L in, like, because everything's LISA in the new consortium, right? And so really we're just the ECS group. But most people are still familiar with us as LECS, so that's why I did that. All right, but the purpose of the ECS group is to gather scientists who are early in their career in order to do many things, including foster collaboration, support career development, promote their inclusion in leadership, and to create opportunities for them to discuss their needs, share their experiences, and just help create a welcoming and inclusive environment inside the LISA consortium. So who is LECS? So the formal definition, I think, is still a little in flux, but at least for now, the definition is basically scientists who either haven't been awarded a PhD yet or have been awarded a PhD during their last 7 years, with that duration subject to adjustments according to career breaks, for example. We currently have 165 members, at least based on the LECS mailing list, and but really, who is LECS is everybody in that picture plus more. So that was a group photo that we took in Dublin when we had a early career scientist meetup. So you can see it's a big group, and I hope any of you who don't see yourself in that photo and fall into that definition, reach out and join us as well. Okay, so now I'm just going to talk about some of the things that we have, some of the things that we do, and some of the things you should do with us. All right, so first off, as the consortium has moved over from Slack to Mattermost, so have we. And we've created a variety of channels for things like sharing papers, posting job postings, organizing the mentorship program, and giving suggestions for talks and things that you would like to see in the LECS talk series. As of last time I checked, I think every single one of these channels has not been used once yet, so please hop over there and, post some papers and job listings. It takes a little bit of time to get the community to embrace these things, so please help me do so. All right, so mentorship program is one of the honestly best programs I think that we have in LECS. It's highly used, and it's something that I really think you guys should embrace. So let me talk a little bit about that. So the idea of the LECS mentorship program is that it connects early career scientists with other senior scientist mentors, and this is a really great way to have somebody provide guidance or just an ear to listen to that's outside of your research group, and I think that can be really beneficial for newcomers to the field. It also gives you another way to connect into the field and kind of broaden your network within the consortium. It runs from September to March. It has training sessions, monthly mentor-mentee meetings, though they're also welcome to do that more frequently, and feedback periods as well. This year we had 31 pairs of mentors and mentees, and from the feedback, people really seem to like it. In one piece of feedback, they commented that their mentors have been a quintessential part of their astrophysics journey. So I highly encourage everybody to either sign up as a mentor or as a mentee. I think it's a very valuable program. And I put on the right what we put as the kind of purposes of this program. So provide personal mentorship for junior LISA consortium members, connect and provide a support network for junior scientists within the LISA community, and create a generally open and inclusive environment within the LISA consortium. I really want to highlight that Florentina's been running the mentorship program the last couple years and has been doing an excellent job, so definitely shout out to her. Okay. So then the other big thing that we do as part of the ECS group is the LECS talks. And this is roughly monthly calls that feature talks of several different types. So over the years, we've had a few different talk series that have been broken up and recombined and things like that, but right now we're putting them all together as part of the LECS talk series. So sometimes this is early career scientists presenting their research. Sometimes it's open source software talks and tutorials to help get the early career scientists more familiar with the tools used within LISA. And sometimes it's professional development seminars. So recently we had one about how to apply for faculty jobs. All these talks are recorded and uploaded to the LISA Mission YouTube channel on a LECS Talks playlist. And so if you scan that QR code, it takes you to that playlist. So you can access some of the previous talks that we've had before. I highly encourage you to self-nominate yourself to give a talk. It is a really great way to have a low-stress environment, to practice giving talks, and to share what you're working on with other people, and hopefully foster some more collaboration if you find that other people are also working on some of the similar things. Okay, now for some things that are more tangentially related to the LISA Early Career Scientist group, but that I still think are worth noting and that kind of tie in. So there's GWEX, which is the Gravitational Wave Early Career Scientist group. And this is an organization of early career scientists across many different collaborations. So that includes LISA. It also includes LIGO, Virgo, the pulsar timing arrays, Einstein telescope, etc. So each of the chairs from each of these organizations serves on the council for GWEX. And so that's kind of how it ties in with LISA. So if you want to get involved with GWEX, it's easy to do so through us. Or if you have things you wish they would do, we're your representatives on that council, so you can reach out to us as well, and we can help make those connections. So it offers many things. GWEX is a really great program. They have job fairs is one of the big things that's been really successful. So whether you are looking for postdocs or grad students, or whether you are looking for a postdoc or graduate position, it connects people and is a really good way to kind of foster it's a job fair. It's great. All right, there's also a number of funding workshops that help you look for things like grants and help you figure out how to apply for postdoc fellowships and things like that. And then relating to that as well, there's just a lot of resources on the GWEX website that references a lot of, career development advice resources, funding resources. They keep a running list of fellowships to apply to and things like that. So definitely take a look at GWEX. It's very helpful. Okay, similarly, something I can take no credit for at all, but that was organized by previous LECS chairs and members. Originally, I had put a bunch of all the organizers' names on here, and then that was too much, so then I took them off, but then I was like, well, that's not right either. And so I do at least want to highlight that Jean-Baptiste was the main organizer for this and put in a lot of work into the LISA school that we had back in 2025. It was a 2-week program, and it covered a lot of the overviews of the different sciences that come into play for LISA. It had tutorials on how to use different tools, and was just all around, everyone seemed to really enjoy it, and it was a great experience for everyone. And their kind of tagline, they can say it better in their own words what the purpose was. So I just grabbed a quote from their site saying the purpose was to gather young researchers interested in LISA science, to foster collaborations, encourage interactions, and train them in the multidisciplinary aspects of the mission and its science. And then what's also really great is all of the recordings from that school are available on their YouTube channel, which I put the tag for, but also if you scan this QR code, it'll take you directly to that channel and that playlist. And so it's a lot of really great resources for early career scientists. Okay, and so then moving forward, a couple things that I just want to highlight. So one, we have the Early Career Scientist Lunch on Thursday. That's a great opportunity to just have a kind of more laid back, casual atmosphere to hang out with each other, talk, decompress a little bit from the conference and get to know each other. So definitely join us for that. And then I want to emphasize the fact that new chairs are going to be taking over. So our election is currently underway, and so the future plans very much can depend on what the new chairs want to focus on. So I anticipate likely continuing things like the mentorship program and the talk series and doing meetups at conferences like this, but also to kind of help them know what you guys would like from ECS. There's a QR code here to a Google form that would welcome suggestions of what would you guys like to see, what would help the ECS group better serve you, and it's pretty free form for suggestions. So please scan that, think about it, and yeah, provide feedback, and hopefully we can continue to grow this group, and thank you all for listening to me.
Thank you, Deborah, and everyone who is contributing to the LECS effort. Do we have any questions? Oh, Shane.
Thank you, Deborah. As you know, I love the LECS group. I think it's really important for what we do. I think a question I always have, which if you can comment on, if you can't at the moment, future comment from LECS would be useful. I feel it's necessary for those of us who aren't in LECS, because we've aged out, to know what we can do to help, ways that we can do better, be more effective, be more interactive, provide support, whatever. So what is it that the rest of us can be doing to kind of help LECS do what they're trying to accomplish?
Yeah, so I think that the big thing that I find this is just my personal opinions and takes on all of this. So one, a concrete thing you could do, sign up to be a mentor. The more mentors we have, the more mentees can be matched to somebody. So, you know, in a concrete sense that. In terms of the broader sense, I think, I don't actually know. I'd have to ask Florentina. But the broader sense that I would say is just that oftentimes it's the early career scientists, the graduate students, the postdocs who are really doing a lot of the hands-on work. And so I think the community is already doing a great job about this, but just continuing to be cognizant of making sure that they get the recognition and making sure that, you know, they get to give some of the talks and that they, I think that's the biggest thing that I think is important. I will say I do think the LISA Consortium's already doing quite a good job with that. It's just a matter of continuing to be cognizant of it.
I was just helped by an early career person. Thank you. Okay, so I just want to make it clear that the Thursday lunch is open to all the early career people here. If you thought, oh, I didn't sign up, you did not have to. You just come to the lunch. And that's one of the things we're trying to do to make sure that early career people can network with each other. But please do show up at that lunch. The information's in the program about which room it's in. Okay, thank you.
Yeah, thank you for that announcement. Very important.
Do we have any online questions?
There's a couple in the back.
There are a couple in the back. One over there, the other one over.
So the grad students who are going to be working on LISA when it launches are in middle school right now. And so I'm wondering if as part of the early career group, we can begin to reach to undergrads, right? You know, people who are maybe starting to think about building a pathway essentially to the people who will be the undergrads, who will then become the grad students, who will help us, you know, manage everything that's coming. Has anyone thought about sort of trying to build stuff for the undergrads of the future, you know, friendly sort of ways in to play with things and model things and just introduce them to the basic ideas?
Yeah. So current undergrads, of course, or anybody involved with LISA is welcome in the early career scientist group, of course. So I'm pretty sure we do have undergrads already in it and things like that. So we have not thought, or at least I have not really thought about using the early career scientist group itself to reach out and do more outreach to high schools and earlier. But that's a very interesting idea. And I, as a person, am a huge proponent of encouraging kind of the scientific mindset and getting people excited from a really young age. I think that's one of the really important things. So whether it be through the ECS group or someone mentioned through the communications group or how exactly we want to do that, I am all for that. And so that definitely seems like something we could look into.
I'm afraid he just said exactly what I wanted to do.
Yeah, to various
I
questions.
do have an idea that one thing you could do is extend your mentor program to undergraduates, especially schools which do not have graduate programs. It's fine for me to talk to students about graduate schools, but I'm an old gray-haired guy. It would be great to have graduate students who are about ready to graduate tell my students this is what graduate school's like, et cetera, et cetera.
Yeah, that's a good point. We could definitely, generally right now the graduate students are the mentees, but we could expand that to make them mentors as well for younger students.
On that question, I'm already recruiting in the daycare of my daughters. So. We have one more question there in the back.
This is more of me sharing my experience than a question. I was part of the first cohort of the ECS mentoring sessions, and I was lucky to have 2 mentors, so I guess that answers the question. We are oversubscribed with the mentors. But I wanted to share that I was an undergrad. I just graduated this year, and for me, it has been a really fruitful experience to talk with both of my mentors, and all the advice that they gave me through applying for grad school, starting on research, and in fact, one of the mentors I'm working with, he is my supervisor now, and I'm presenting on that. So it's I think this program is really useful for undergrads, and I totally support that. If more communication should be involved in getting more people as mentees into that. Yeah, thank you.
Thank you for sharing. That's fantastic to hear.
We have a question online from Kim Curry. The question is, are mentor-mentee relationships one-on-one or many-to-many?
So I think they're roughly one-on-one, but sometimes they're like one-on-two. Like some people have two mentors. I am not entirely sure if we've had situations where one mentor has multiple mentees. I think maybe it depends on if it's oversubscribed. The goal is roughly a one-on-one type of relationship.
I can say the comment is, context, I'm not a scientist. I wouldn't be a good single mentor for an early career scientist.
I'm sure that we have, can be flexible if somebody wants to be a mentor, but maybe doesn't feel comfortable being their only mentor. Oh,
there is one more question in the middle.
I was just wondering, so for this type of group, is it only useful if you want to stay in academia? Or because from what I've been hearing, it's mostly postdoc, grad school, or I guess I was wondering if I could find any use to it if I already know I want to go into industry.
Yeah, so definitely a thing to scan and put comment on of what maybe you're looking for, because so the mentorship program, since we're asking other people in the community, you're getting mostly other, people who've gone faculty or postdoc route. That doesn't mean that they can't answer questions and help and know people, and maybe they're like, oh, some of my graduate students went to industry, I can connect you to them. So I think the mentorship program could still be useful, even though it's probably more aimed at people staying in academia. The group as a whole, though, the LISA Early Career Scientist group, definitely still join. It's something that I think could definitely be useful for people trying to go into industry as well. It's just a matter of us figuring out who should give talks. Maybe we can find, I know people who were gravitational wave scientists who are now in industry, so if I know people are interested in that, then I can reach out to them and ask them, hey, would you like to talk about how the interview process was and how it's been transitioning into industry and things like that. So we're very open to whatever we feel like, whatever the community feels like would best help them. I think since many of us are in the mindset of academia, we don't necessarily think about that. So this is definitely a reach out to us and tell us what you would find helpful, and we'll be happy to foster that. Great.
Let's thank all the speakers of this session.